So welcome everybody joining us on YouTube. So today is April 13th, and this is, for the first part of this, we're going to go through some more implicit differentiation. We'll do an example or two before we move on to chapter 3. All right, so when I look at this one, we had just talked through the idea that we are going to see a few things. So taking the derivative of this left-hand side is not a problem. But all of the complicated stuff is going to happen over here on the right. So we're going to have a chain rule that we use. And then when we take the derivative of xy squared, we're going to use product rule. And then we're going to use another chain rule over here. Okay, so let's go ahead and step one. I'm going to go through and replace all of my y's with f of x's. So we'll be left with something like this. 5 plus 2x equals sine of x times f of x squared. Okay, so you get something that looks like this. And now I'm going to go and take the derivative. So on the left-hand side, we're going to get 0 plus 2, right? So the left-hand side is just going to be a 2 after I take the derivative, right? So I'll make myself a little note here. We're taking the derivative. And now we're going to work out this whole thing. So in my chain rule, I'm going to take the derivative of sine, which gives me cosine. And on the inside here, I'm going to leave my inside function alone. Right? So we're going to get x times f of x squared. But now what I'm going to have to do is I have to multiply this by the derivative of the inside function. Okay, so this is going to end up being a chain rule. A product rule. So we're going to have 4 parts that we have to consider. Okay, so I'm multiplying by the derivative of the inside function, and then we're going to use product rule. So as we go through, I'm going to think about my two pieces. I have an x and I have an f of x squared. And so on the first pass, I'm going to leave my x alone. Okay, and then what I'm going to do is I'm going to multiply by the derivative of the next function. So when I take the derivative of f of x squared, I'm going to have to use chain rule. So I get 2 f of x times f prime of x. Okay. And then on the next piece over here, what I'm going to do is I take the second part. So I'm going to leave this f of x squared alone. And then I multiply by the derivative of x, which is just 1. Okay, so in each piece, you can see that in this piece, I leave the x alone, multiply by the derivative of f of x squared. Then I leave the f of x squared alone and multiply that by the derivative of x. Okay, so as I'm scanning through here, I notice that this is where I have an f prime, and that's it. So this is a chain rule here because we have an inside function, right? So this is going to be when I take the derivative of this piece, okay, I'll box it in green, okay? So we're thinking about y as its own function. That's why I replaced it with f of x. And so when I take the derivative, I have a composition here. I have a squared term. So we have your outside function is squaring, and then you have this inside function, which is f of x. Okay, so that is a composition, so we'd use chain rule. All right, so now what I need to do is I need to solve this thing for f prime, right? So I've taken all my derivatives, everything is done. And so what I want to do is now algebra, okay? So just for ease, what I'm going to do to start here is I'm going to replace all my f of x's back with y's. I just think it's easy. It's going to be easier to follow that way. Okay, so we're going to get 2 cosine xy squared times, and then over here we'll get 2xy times y prime plus y squared. Okay, so I want to give you all a moment to just process this. Okay, so this x and this x, right? So I have a 2x, and then this is a y, and this is a y prime, and then this is y squared, times 1, which just gives me y squared. Right, so taking this whole thing, I can simplify it just by replacing my y's again back down to this. Okay, so now our job is to solve this for y prime. Okay, so step 1, I'm going to expand everything. So I get 2 equals cosine of xy squared times 2xy y prime plus cosine xy squared times y squared. Okay, so again, we're still tracking this term right here, right? That's what we want to solve for. So I'm going to do this in 2 steps. I'm going to bring everything that doesn't have the y prime over to the left, and then I'm going to divide to get what I want here. Right, so let's go ahead and give ourselves a little bit more space. So I'm going to bring this term over to the other side. So I get 2 minus cosine xy squared times y squared equals cosine of xy squared times 2xy y prime. Okay. And then to finish this off, I'm going to divide both sides by this, okay, to get y prime by itself. And then so what we should end up with is 2 minus cosine xy squared times y squared divided by cosine xy squared times 2xy equals y prime. Okay, and so then this should be our derivative. Now, one note, so one question that came up was this y prime is also the same as dy dx, right? So if you want to think about it this way, there's 2 different notations. This one is a dy dx. We used a y prime, but they mean the same thing. Okay, so I'll pause here for questions. Questions just yet? Comments, concerns? Yeah, so when I expanded, so I'm only talking about this step right here. So we took this, yeah, and we distributed it to both terms. Yep, so that we did, yep, I distributed that through to both pieces there. Okay, is this one good so far? Any questions along the way? Just to get it, I can zoom out so we can get it all on one screen, right? So if you wanna follow along the whole thing here. All right, so this will be on the video. So if you want to go back, take a look at it. Okay, so what do we think? Is this good? Do we want to move on to chapter 3, or are we still having some trouble with this implicit stuff?
Is this where we're cutting off for the exam, or are you going to have chapter 3 stuff on the exam?
No, there's no chapter 3 stuff on the exam. Nope. So the exam has already been written. It's done. It's up. It's open. And it's only chapter 2. So there is can we do one with a point? So Bella, do you mean one with like where it says find the equation of the tangent line?
Yeah, like one with a specific point for the tangent line.
Okay. Do you want to do a whole another one, or do you want me to put a point on this one?
I guess we could put a point on this one. Sure.
Okay. So if we think about this, let's go ahead and so I'll downsize this and put it off to the side. So we could put a point. We could figure out a point that goes on this. So as I'll just sort of, I'm just going to make this up here, but so oftentimes when I'm thinking about these, I want to find a nice value. So so sine is a tricky one because you know there's not a whole lot of nice values that end up popping up. But 0 is one that we can play around with. So if I make my y coordinate 0, then I have to sort of find an x coordinate that goes along with this. And so when y is 0, that means I'm going to, no matter what x is, I'm going to get sine of 0. And so this is 0. So I just have to pick an x that will make the left-hand side, right? I have to pick an x that makes this 0. And so a point that might be there is -5/2. So let's bring up Desmos, and we'll type this thing in. So 2 plus 5x equals sine of xy squared. This one is a mess. All right, so I want to share this with you all because this one's something. Okay, so this is what our implicit curve looks like. Yeah, but we should have this point -5 halves, comma 0. Oh, yeah, right. Yeah, so these implicit curves. So as we zoom out, so see how it gets all garbled up here. So we're pushing the limits of the graphing calculator here. So this isn't really what the curve looks like, but it tells you that there's really a lot going on, and the calculator's having a hard time keeping up with it. So the curve, if we sort of zoom in, it is a little bit smoother, but it kind of looks like a scribble, right? It looks like this squiggly line. Okay, so oh no, what is our equation? 5 plus 2x. 5 plus 2x. I made a mistake here, right? So it should be 5 plus 2x. This is gonna be similar like this, right? So here's what our equation looks like. Pretty messy. So what we should find here, right? So just looking at it visually, we should find that, I think we're going to find that we have a vertical tangent line. Okay, so what we're going to do is we're going to jump back over to the Blackboard and see if we can do some algebra here to figure out what's going on, right? So the equation looks like this, and now what we're going to do is we need to find a slope, right? So the typical equation would go something like this. So we would have y minus 0 equals some slope times x plus 5 halves, right? If we wanted to find the equation of this thing. And so what we need is we need to determine this slope. So what we're going to do is we would come down here, right? So we would go down to our y prime, and we would plug all these values in, right? So we would say y prime equals, right? Oops. Right, so I'm gonna give myself some space here. So it'd be 2 minus cosine of, we'd have -5/2 times 0 squared times 0 squared, all divided by cosine of -5/2 times 0 squared times 2 times -5/2 times 0. Okay, so you'd plug all of these in, and what you end up seeing here is this is going to simplify the numerator. This is being multiplied by 0, so the numerator you're going to get 2, and in the denominator you're going to get everything is multiplied by 0, right? So what you're going to end up getting in the denominator is 2 divided by 0. And then what this means is you have a vertical tangent line, right? So we saw the other day that, hey, if you ever divide by 0, right, that means that your tangent line is going to have a vertical slope. And so in this case, what we see is that, hey, that's going to be a vertical line, and it's just going to have the equation x equals whatever, right? So the equation of our tangent line in this particular case is going to be x equals -5/2, right? So that would be the equation of our vertical line. And then jumping back over to Desmos gives us, right, so if I just look at this vertical line, x equals -5/2, right, we can see that just as we suspected, right at that point there, we would get that vertical tangent line. Okay, so Bella, this wasn't exactly the typical example, but when we make stuff up, sometimes that happens. So, all right, so do we want to do another one? How do we feel? I know we've got 6 of us here, but is it good, bad? We feel prepared for the exam? Caleb's good. Luke feels good. Okay, so what I'll do, I mean, I'm always available for questions, right? You can always send me questions and anything like that. But for this time, we'll go ahead and we will we'll push ahead and we'll take a look at our next chapter. Okay, so moving on to chapter 3. So what we did is this was 2.7. That was the end of exam 2. We're going to skip section 2.8. For those of you going on to take Calc 2, you'll revisit these ideas in Calc 2. And so then we're going to start doing chapter 3. So this chapter, you'll notice that the trajectory of the class so far has been chapter 1. We did a lot of conceptual understanding of the derivative. What does it tell us? You know, what kind of information can we get from it? Trying to understand rates of change and how we measure them. And then we moved on to chapter 2, which was, hey, how do I compute these things, right? So I have all these different functions, and then there's going to be rules for computing them. So we went through this this section of the class where we were doing a lot of computations, right? So just compute this derivative, here's a new rule, compute this derivative. So we're done with that now. So this is a new set of ideas where we're going to start saying, all right, we understand what the derivative measures, we know how to compute them, so how do I take all those ideas and put them into context around these things? So one of the contexts that we're going to see is what we do is we ask ourselves a lot, how do I optimize life, right? How do we find the most efficient route to do something, or how do I make the most money, or how do I minimize the waste in this process, right? So we often want to maximize something, or we want to minimize something, and so that's one of the big areas for calculus, right? So you'll see we call this optimization. And so what we're going to do is we're going to try to think about, hey, how do I optimize, right? So if I'm given this situation, how do I get the most out of it? How do I maximize profit? How do I minimize waste? How do I maximize time? How do I maximize productivity? Things like that. So if we can quantify them, then we will try to use calculus to find these optimal values. All right, so what we're going to do today is we're going to look at these things graphically and try to get some language around these ideas so we can start to talk about them more effectively. All right, so the first thing that we're going to talk about here is this idea of something being a global or absolute maximum. Okay, so what this means is you are the best, right? This is, if you are the global maximum, you are the absolute best point around. You can look over the entire domain, and there's not a single other thing that is better than you are. And same thing for minimum, right? So sometimes I say best, maximums aren't always best, right? So maximizing waste would be really bad. So sometimes the minimum is the best. But absolute maximum means that, you have an output that is at least as big as every other output. So there could be things that match you in terms of output, but nothing is bigger. And then same thing for minimum. You have the smallest possible output. There are other things out there that might be able to match you, but nothing has a smaller output than you do, right? So these are the ideas of global or absolute max and min. And then we have this idea of what's called a relative or local max and min, right? So I like to give a story about local and global maxes and mins that I think at least it helps me. Okay, so being a local maximum means you are better than everything else that is close to you. Okay, so you can be a local maximum on a lot of different venues. So when you think about this, I like to use a basketball analogy. And so you can think about being a basketball player in your town, and the idea of being the best basketball player in your town, right? So whatever town you live in, you could be the best basketball player, right? So if you go around your town, there's nobody that's better than you at basketball. But that doesn't necessarily mean that you're the best basketball player in the state, right? So there could be somebody who lives in a different town that's better at basketball than you, but in your own particular town, you could be the local maximum, right? So you could be the best basketball player in your town. So you would be this local max. But you could flip this on its head and say, well, maybe I'm not the best basketball player in my town, but we could look closer, right? So you could be the best basketball player that lives on your block, right? Like, hey, on my block, I'm the best basketball player. Maybe somebody else that lives a block over there, they have a better basketball player, but on my block, I'm the best. That you would be the local maximum player on your block. You could even go more refined, right? So maybe you're not the best basketball player on your block, but maybe you're the best basketball player that lives in your house, right? So close to you, if you look around, everybody in your house, you're a better basketball player than them. But maybe in a different house, there's somebody better, right? So this is the idea of being locally the best. Everything that's close to you, and you get to sort of define what close is, right? So anything that's close to you, you are there. But we don't want you to be the only person in that interval, right? So we want to make sure that there's other people in that interval. On the other side, on the global max, right, no matter where you look, if you're the global max, it doesn't matter what town you go to, doesn't matter what continent you're on, right? If you're the best basketball player on the planet, doesn't matter where you go. You can look everywhere, and there's not going to be anybody that's better than you, right? So this is sort of an analogy that I think about between local max and global max, or correspondingly minimums, right? So if we look at these pictures right here, this point right here, this would be the global maximum. So if you look at the blue line, there are no other points that achieve a higher output than this one, right? So this would be our global max. Turns out it's also a local max, right? So if you're the best basketball player in the world, you're certainly the best basketball player on your street, right? So global maxes are also going to be local maxes. All right, now if we come over to this graph over here, this point, G of A, would be considered a local max, right? So if I look at everything that's close to it, a little bit to the left, a little bit to the right, those values are lower. So this is a local max, but it is not a global max because there are other points over here that achieve a higher output, right? So this would be a local min. It is not a global min because there are points elsewhere that achieve a lower value. And then this is a global max, right? So if I look everywhere in my domain, there is no other point that achieves a higher value. So this is both a global max and a local max. Okay, so what we're going to do is we're going to think about how do I look at these things visually, and how do I identify when are these going to occur. Okay. So what I want to do is I want you all to think through this preview activity 3.1.1. So let's go ahead and let's take 5 minutes. So I'm going to put us, we have 6 people. So let's we'll break off into 3 and 3, and then talk in a small group through these A through H. So we're going to go through and identify where we find local and global maxes and try to come up with some conditions for when they would exist. Okay, so I think we know how this works. So we'll go into 2 rooms. Everybody will be 3 and 3. And so talk through these A through H. And then we'll come back here at 10. Right, so you have 7 minutes.
To try to like share my screen so that we can see the book.
Hello. I think screen sharing is great. That's all I heard. Yeah, definitely share your screen.
I forgot I was still muted. But right now I'm trying to dual screen, so if you can do that. So.
Perfect. All right, so did that make sense to everybody with this idea of local versus global max? And
Yeah.
Hello?
all right.
I couldn't hear because like my dad's phone was ringing and my brother was talking, so I couldn't like pay attention. It was really loud. Good. We're looking at the 4th point. Oh, the 4th one.
My brother is also in class across the
Over
table
to
right
the
now.
3 and up to the 9.
Yeah, I have no intentions. You know, this stuff pops up, and it's interesting, and they tap it. Yeah, that's but thanks a lot for calling.
All right, so we have, so go ahead and basically the questions are this, right? Identify the local maxes, the local
That's fine. It's
global maxes.
on that truck. That was
It might be good to use like the annotate feature, right? So if you went and you found like a point like this one,
yeah.
you might just be able to like all draw on the graph and say, hey, this is our, this is a local max. Right, so go through identify them and see if we can pick those up.
Email that.
All right, so I'm gonna jump into the other. Excellent. I like the screen share here. So any questions so far? We feel okay about it?
Yeah, we're on C right now.
C? Okay. So remember we have the annotate. We have annotate, right? So you can go through and circle.
How do you do that?
So up
Top
at
your
the top,
screen.
you would click on annotate. So you have, Riley, you're sharing. So you should have a big button up there that says annotate that you can click on. Everybody else, you click on view options and then there's annotate. Yep, exactly like that. So we can all draw on this, and then so if you want to point to this, right, you could say, hey, this is the global max, right? ideas like this.
So would that also be the local max?
It is both, yeah. So if you're a global max, then you're also a local max. Now, so we'll talk about this when we come back together. There's an idea here that is a little bit different, yeah. So this can get a little bit confusing when you talk about endpoints.
So global max, would you use the full coordinate 1, 2, or would you just use the x value or just the y value? Or
So I think it's helpful to just think about it as a sentence. So you would say that the global maximum value is 2, which occurs when the input is 1.
okay.
Right. So I think number sentences like that are really helpful. So it depends. It depends on exactly what's being asked for. So if you're going to find the inputs, then you would say that the input that it occurs at is 1, and sometimes you're asked for the value, like the output, and so then you would give the value 2. So it depends on what question is being asked, but you have to consider that. So if they're asking for where does the global maximum occur, it occurs at 1. If they're saying what is the global maximum value, the output would be 2.
Okay. So how would you do the minimum if the graph doesn't seem like it ends? Are those actual endpoints or?
So it tells you on the interval -3, 3, right?
Mhm.
So it says, does it have a global max on -3, 3? So you would stop here and here, and it's giving you that these endpoints, right? So since these are squared, that these endpoints, I would say, presumably are here, yeah.
Okay.
So when you look around, it says, does it have a global maximum? And then D would say, does it have a global minimum? So what do you think? We talked about the maximum, right? But what would the global minimum be?
Wouldn't it be a negative?
-3.
Go ahead, Riley. What did you say?
Wouldn't it be a -3?
It would be at -3, yeah. So X would be -3, and then what would the output be?
-3.
Yeah, also, right? So they're both the same, right? So this would be -3, comma -3. Yeah, so the global minimum output is -3, which occurs when you have an input of -3. Okay. So what we're going to see in parts E and F here is we can actually use the derivative to help us identify some of these questions, right? So how do I look at these points? Visually, right, if I can graph it, this is something that's very nice. But what we'll see here in a little bit is we're not always going to be able to see the graphs exactly. So we're going to have to rely on the derivative to help us identify where these points are, right? So go through E, F, G, H. We've got 1 minute. So think through these for another minute, and then we'll all come back together, okay? I'm going to jump into the other breakout room just to check in with them one last time. Hello. We're back. Do we make it through all of these?
On
I'm on
G
G.
right now.
G. Okay. Excellent. What do you think?
I think G would be true. Because at the local max at -2, it's non-differentiable, so it does not exist. And then same for X equals 0. And then the derivative is like a horizontal line at 1. So that's also 0.
Mm-hmm. Yeah, so notice that they use the word relative here and not absolute. Right? So sometimes like there's a tricky thing that can occur when you're at endpoints. So yeah, you're right. So this one, G is true. What about H? H is, do you have an example where H is always true, or?
I think H is false because at 1.5, like that's not differentiable. but like it's also not a maximum or a minimum.
Right. Yeah. So that's an example where it doesn't have to be, right? So just because the derivative is 0 or does not exist doesn't necessarily mean that we're going to have one of these maximums. Right. So what we'll see here in a little bit is that we have this nice test which says the derivative being 0 or not existing sort of gives us candidates. Instead of looking over the whole graph, we can just look at a subset of points, specifically where the derivative is 0 or not exist, to give us just candidates to check. Okay. All right. So I'm going to close out these rooms and bring us all back together here. All right. So we are back in the main session. So I think everybody is back in. Yeah. Okay. So let's jump back over to our book to share this. And so as we went through it seems like we all were able to identify, hey, local, global maxes, right? And so as we go through here, so we can pick out some points. So right, -2, this is going to be a local or a relative max. This will be a relative and also the global max. And then we have a relative min, and then our global max is going to occur over here. So depending on the author of the books, there's some ambiguity over whether or not you want to call an endpoint a global max or a relative max or relative min. And so you'll notice that in this definition here, so the author of this textbook, Active Calculus, he says, we say f of c is a local maximum if it's smaller than everything for all x near c. So when we think about precision, this idea of being near, like, what does that actually mean? Okay, so there is a more technical way to define this nearness that we are purposefully not talking about here. So it's just unnecessarily complicated. So with this language though, right, so if you're an endpoint, you could be thinking about, hey, everything that's near you, right? So you could, if you're at this endpoint, the stuff that would be close to you would be over here and you're smaller than it, right? So you'd also be you'd be a local minimum. But some authors, and so this sometimes comes out in web work, they want you to be able to check on the other side as well. So you want to be able to check to the left and you want to also be able to check to the right. So there is a little bit of ambiguity here when you're looking at endpoints. So sometimes authors will say endpoints cannot be a local minimum or a local maximum. So endpoints a lot of the time are considered only in the global sense and not in the local sense, just because you can't check on the other side, right? So for the endpoint, on the left endpoint, you can't check anything to the left. So there's some ambiguity that could happen there. So just keep that in mind, right, as you're going along, that a lot of authors don't want to consider endpoints as local. Okay. But big picture here, right? So what we were trying to do is we were trying to go through and identify, hey, is there a condition for us to be able to check where we're going to have local maxes and global maxes and all that? And so we should have identified that, hey, yeah, this is true, right? So every relative maximum and minimum occurs when h is 0 or does not exist, right? So when I looked at this point up here, the derivative is 0. And at these corner points, right, the derivative does not exist here, right? So it doesn't exist here, it doesn't exist here, and then up here it's 0. So that's nice. But if you look at all the different points where h prime of c is 0 or does not exist, it doesn't necessarily have a relative max or min, because this corner point, the derivative does not exist here, and that is neither max nor min. And then same over here at -2.5, we would have a horizontal tangent line here, but it's neither a maximum nor a minimum value. right? So it gives us a candidate. This idea of the derivative being 0 or not existing gives us a candidate to check, but it doesn't guarantee that we're going to have this extreme value. Okay, so this is a nice helpful graphic in the book that shows us sort of different scenarios, right? So here's a scenario where we could have a derivative that is 0, but it's neither a max nor a min, right? But then in these other cases, we have a max or min at each of them. Okay, and so one important definition here, right, is this idea of a critical number. So we're talking about, hey, where do derivatives be 0 or where do they not exist? We call these critical numbers. So anytime you're asked to find critical numbers, you're trying to find the points where the derivative is 0 or the derivative does not exist. Okay? And so what this is going to do is it's going to allow us to go through, if we identify all the critical numbers, then we're going to test, hey, is this right? So is this thing a maximum or minimum value? Okay. So let's go back over. So this idea, I wish I could dual screen here, but this is the idea of the first derivative test. Okay, and it says you're going to have a relative max if and only if the first derivative changes sign, either goes from positive to negative or negative to positive, right? So what we're going to do is we're going to go through and we're going to test if our derivatives change sign at particular points. So this, I don't think, is a very helpful graphic, so I'm going to draw a little bit more on the blackboard to illustrate this phenomenon. Okay, so for me, I think the first derivative test is sort of better as a picture. All right, so so what we have, right? So this is, we're just going to call this the first derivative test. Okay, so the first derivative test says, hey, you're going to have a local maximum value. Okay, so what we're going to do is we're going to have this point C, right? So we're going to have a local max at a critical value only when, if you look at one side of it, it goes increasing, right? So this graph is increasing to the left of the point and it's decreasing to the right of the point. Okay, so we have a point here where the derivative is 0, right? So that's 0. And then over to the left of it, we have that the derivative is positive, and on the right of it, the derivative is negative. Okay, so when you're going through and you're checking your points, you're going to say, hey, I found a critical number. And then what you're going to do is you're going to look a little bit to the left and a little bit to the right. And if it goes positive on the left and then negative on the right, you're going to have a local max. And then correspondingly, you can do the same thing if you have a local min, right? So you have this value C, and this is what a local min looks like. And so what you're going to do, you find this point where the derivative is 0, you're going to look a little bit to the left, and you're going to say, okay, my derivative over here seems to be decreasing. And then over here on the right, my derivative is negative and then positive, right? So what this corresponds to is our graph is decreasing to a point, and then all of a sudden it turns around and then it's increasing out of that point, right? So using derivatives, we can go through and use this test to figure out, hey, where are our local maxes and where are our local mins? Okay, so let's go ahead and with our last minutes here, let's do a quick example. Okay, so let's go ahead and let's do something like find critical numbers, right? So for critical numbers, we would want to identify any time where the derivative is 0 or does not exist. Okay, so what we're going to do is we're going to take the derivative of this function, and we get 3x squared minus 4. And we want to know, hey, when is that equal to 0? Okay, so I'm going to go ahead and solve this for x. So you'll get x squared is equal to 4/3. And so x is equal to plus or minus the square root of 4/3. Okay. Now, if we're going to go ahead and then use the first derivative test, we could try to identify at each of these values, do we have a local max or do we have a local min? Okay, so what we're going to do is we're going to set up what we call a sign chart. And we are going to go ahead and think about these values. So what we're going to do is this is going to be a sign chart for the derivative. So going back to this screen, what I want to know is if I'm to the left of a critical value, is my derivative positive? And then if I'm on the right, is it negative? Right, so we're only going to be concerned as to whether the derivative is positive or negative, not whether we have what the value is. So we only care if it's positive or negative. Okay, so what we're going to do is we're going to go through and we're going to pick points inside of these different intervals. And so if we think about this, so this would be, say, 0, right? So 0 is a number that lives between negative square root of 4/3 and positive square root of 4/3. So to help us out here, if you want to think about it this way, you could think about these as numbers. So this is about 1.15 and negative 1.15. Okay, so approximately. So what we can do is I can pick another value that's bigger than 1.15, say 2, and over here I could pick negative 2. And so what we want to do is I want to know if I plug, right, if I plug my values over here back into the derivative, do I get something that's positive or do I get something that's negative? Okay, and so what happens is if I plug in negative 2, right, so f prime of negative 2 is going to be 3 times negative 2 squared minus 4 is 8. Okay, so this is going to be positive. Similarly, if I plug in 0, I'm going to get negative 4, so this is negative. And when I plug in 2, this is going to be positive. Okay, so putting this all together, right, if we go positive to negative, right, increasing to decreasing, what I should see is that I have a local max right here, and then I'm going decreasing into increasing, so I should find that I have a local min right here. Okay, so putting all this information together, we're finding critical numbers of this function, x cubed minus 4x, and we should see that, yeah, my local max is at negative square root of 4/3, and my local min is at positive square root of 4/3. And so just to wrap it up here, let's just take a look at the graph. So here's our graph, x cubed minus 4x, and we should see that, hey, yeah, we do have a maximum here as we predicted, and a minimum here. So one of the conditions here that's a little bit different is you might ask yourself, hey, well, couldn't I just graph this thing? All right, we could, all right? So x cubed minus 4x, if I wanted to find the local maxes and mins, we could just graph it, okay, which is absolutely right. But as I alluded to, sometimes we're not always going to know what the graph looks like. So in the next section, we're going to introduce this idea of a parameter. So you're going to have x cubed minus ax, where a is just some number, and you're going to get a family of graphs, right? So your graph could be any of these things, right? So anywhere in this family, if my graphs look like this, I should be able to identify, right? They all look pretty much the same, so I should be able to track these points. And no matter the value for A, I should be able to figure out what these maximum and minimum values are and where they occur. So without knowing what A is, it's really hard for me to say precisely what the graph is. but we'll use the same process with a parameter in it to figure out more generally what do these things look like. Okay, and so there's a quick example. So what we'll do on Wednesday is we'll jump in and we'll do lots more examples with this, and we'll look at some other tests as well. So one's called the second derivative test. But we are way over today. We're 7 minutes over. So I'm going to call it here. But don't forget about the exam. So find 2 hours throughout the week to sit down and take the exam by next Sunday night. And as always, email me if you have any questions. So stay safe, everybody. Stay healthy. I'll see you around.